right, how's it going? Going. So any questions? All right, well, we were talking number theory. Everybody okay with Euclid's algorithm?
Everybody gets a
All right, well, let's continue developing this stuff. So we're talking modular arithmetic. Remember, the idea of modular arithmetic is we can take the whole set of integers and we reduce it down to a small finite set of modular equivalences and then operate on those equivalences. And this can be useful for doing what would otherwise be really large calculations. So there's a technique called modular exponentiation. And this is a way to calculate large exponents, something raised to a big power modulo something else, without doing too much work. So for example, (14 raised to the 131st modulo 13). And I happen to know that this is going to be congruent to 1, mod 13. So 14 raised to the 131 minus 1 is this big long number. And if I take that big long number and divide by 13, I get an exact integer. So 14 to the 131st is one more than a multiple of 13. Now, how did I know that so quickly? Because if I think strictly in terms of modulo 13, what is 14 congruent to? One more than a multiple of 13. So 14 times 14 is congruent to 1 times 1, because we can multiply congruence classes, and it's the same thing as multiplying numbers and then reducing, right? This is another way of saying 14 squared is congruent to 1 squared. And if I multiply by 14 again, 14 cubed is congruent to 1 cubed. And in general, 14 to the n is congruent to 1 to the n. So 14 to the 131st is congruent to 1 to the 131st. And I know what 1 to the 131st is. It's just 1. Okay? So I did not have to multiply 14 by itself 131 times and then divide that by 13 and see what the remainder was. We switch over to a modular equivalent, and our calculation became very simple. Okay, so we can generalize this. I picked this because I knew 1 to the 131st would be easy to calculate. But we can generalize this. So suppose I wanted to do, I don't know, 11 to the 131st modulo 7. Well, it's a little harder now, right? So 11 to the 0 is just 1. 11 to the 1 is just 11, which is congruent to what mod 7? That's 4. So 11 squared will be congruent to 4 squared, which is 16, which is congruent to what? 16 mod 7. 2 more than 14. Now I can do this 131 times, and I'm never going to have to work very hard. right? In fact, 2 squared is going to be 4, 4 squared will be 16, which will be 2. I'll just keep alternating between 2s and 4s. I've got to do a little bit of work, but I don't want to do that little bit of work 131 times. That's still a lot of writing to do. So here's what I'm going to do. I'm not going to calculate every power of 11 all the way up to 131. I'm just going to calculate the powers that are powers of 2. So I'm going to take 11 to the 2 squared, which will be 11 to the 4th, and that's going to be congruent to 2 squared, which is 4. And then 11 to the 4th squared will be 11 to the 8th, and that'll be congruent to 4 squared, which is 16, which is 2. And I've got a pattern now, right? 11 to the 16th is going to be 4, 11 to the 32nd will be 2, 11 to the 64th will be 4, and 11 to the 128th will be 2. And I'm just following the pattern. Well, my goal is to find 11 to the 131st. Okay, this is where the exponentiation part comes in. So 131 I can write as a sum of powers of 2. If I don't know how to do that, convert it to binary. That tells you where the powers of 2's are. This is 128 plus 2 plus 1. So 11 to the 131st is 11 to the 128 plus 2 plus 1, which law of exponents tells us is 11 to the 128th times 11 squared times 11 to the 1st. And now I just fill in from my table up here. 11 to the 128th is congruent to 2, 11 squared is congruent to 2, and 11 to the 1st is congruent to 4. So this whole thing is congruent to 2 times 2 is 4 times 4 is 16, which is congruent to 2 mod 7. So 11 to the 131st is congruent to 2 mod 7. And I had to do 1, 2, 3, 4, 5, 6, 7, 8 squares. And then I had to add them together and multiply their equivalences. Right? And I certainly did a lot less than 131 repetitions of something. So 11 to the 131st, let's see if we did it right. Minus 2, and this should be a multiple of 7, and it is. So that's what modular exponentiation is. Right? You basically write your exponent as a sum of powers of 2, and then you calculate what your number raised to each of those powers of 2 is, and then you multiply out the relevant terms. And it's considerably less work. If I wanted to raise something to the billionth power, I would just need to fill out 30 of these and then multiply whichever ones corresponded to the binary expansion of my number around a billion, and I'd have my answer. It's a really powerful way to calculate large exponents, calculate what large exponents are congruent to. Yeah?
Can you go over that expansion again?
Yeah. This one?
Yeah.
So do you agree 131 is 128 plus 2 plus 1?
Yeah.
Okay. So 11 to the 131 is 11 raised to this.
Okay.
Right? And there's this law of exponents which says, you know, x to the a plus b is the same as x to the a times x to the b. Right? So this was 11 raised to the 128 times 11 to the 2 times 11 to the 1. That's where that came from. That's the cool thing about exponents. That's what makes slide rules work. So I don't know, pick some numbers. So 5 raised to the 200th modulo 13. This is going to be a bad one, I can tell. So we need to do two things. We need to write 200 as a sum of powers of 2. Well, if you have a hex calculator, you can convert 200 to hex and write it out in binary. So it's 128. I'm going to cheat. And 64. 32, 16, 8, 4, 2, 1. So that's 200 in binary. So 200 is equal to 2 to the third plus 2 to the sixth plus 2 to the seventh. Where did my screen go? There we go. Alright, so that's 200 in binary, which means it's 2 to the 0, 1, 2, 3, plus 4, 5, 6, plus 7. So 5 to the 200th is 5 to the 8 plus 64 plus 128, which is 5 to the 8th times 5 to the 64th times 5 to the 128th. And now we have to write what each of these things is, modulo 13. So 5 to the first is 5. 5 squared is 25, which is 1 less than 26. So I'm going to call that -1 because that's easier to work with. 5 to the 4th will be 1. 5 to the 8th will be 1. 5 to the 16th will be 1. All of these are going to be congruent to 1.
Does having negative remainders violate the division algorithm?
No.
Doesn't.
No. The division algorithm says we could find a positive number between 0 and 12.
Oh, okay.
But it's still congruent to -1. And that's easier than doing 144. Or, 12 and squaring it to get 144. Alright, so 5 to the 200th is 5 to the 8th times 5 to the 64th times 5 to the 128th is congruent to 1 times 1 times 1, which is just 1. So 5 to the 200th is 1 more than a multiple of 13. So that's a multiple. So that's modular exponentiation. It's one of the tricks we use to do big arithmetic like this. The other trick we can use is something called Fermat's little theorem. Different FLT from Fermat's last theorem. So Fermat's little theorem says the following: if P is prime, and P does not divide A, then A to the P minus 1 is congruent to 1 modulo P. Okay, P does not divide A, it just says A is not a multiple of P, because if A is a multiple of P, then it's divisible by P, and so any power of it is also divisible by P. So that's kind of a degenerate case. But ignoring that uninteresting case, basically if you take a prime, anything raised to prime minus 1 is 1 more than a multiple of that prime. So for example, 5 to the 6th is congruent to 1 modulo 7. So is 4 to the 6th, and 3 to the 6th, and 6 to the 6th, and 2 to the 6th, and 1 to the 6th. If fact, anything to the sixth is congruent to 1 mod 7, except for multiples of 7. You know, 5 to the 10th is congruent to 1 modulo 11. So is 9 to the 10th. So is 2 to the 10th, and so on. Okay, well, this is also useful for dealing with large exponents. So we know that 5 to the 10th is one more than a multiple 11. Suppose we want to find 5 to the 1002 modulo 11. Okay, 5 to the 1002 is a big number. If you happen to have a calculator, you can divide by 11 and figure out this is going to be congruent to 3. But if you don't have a big calculator, how can we figure this out? Fermat's little theorem will let us chunk away at this exponent. So if we're working mod 11, what do we know from Fermat's little theorem? We know 5 to the 10th is congruent to 1 modulo 11. That's Fermat's little theorem. Having something congruent to 1 is really nice, because if we raise this left side to any power we want, it'll be congruent to 1 raised to that same power, which is still just 1. Right? Ones are nice to deal with. So if I take 5 to the 10th and raise it to the 100th, that's congruent to 1 to the 100th, which is still just 1. But what is 5 to the 10th to the 100th? That's 5 to the 1000th. So we can play with laws of exponents. 5 to the 10th to the 100th is 5 to the 10th multiplied by itself 100 times, which is 5 to the 10 added to itself 100 times. So this general law of exponents is x to the a to the b is equal to the x to the a times b. So by using Fermat's little theorem and just multiplying 10 by 100 to get 1,000, we can conclude 5 to the 1,000th is congruent to 1 modulo 11. We're after 5 to the 1,000th too, but we're only 2 steps away from that now. So we can do those by hand. 5 to the 1,001 is congruent to 5. 5 to the 1,002 is congruent to 5 times 5, which is 25, which is 3 more than 22. It's congruent to 3. So those are 2 main tricks that we can use to do large exponentiation. Modular exponentiation or Fermat's little theorem. And there are particular cases of this more general principle, which is we can reduce things modulo whatever we're working in anytime we want, and then operate on those. So when I was a kid, I was always trying to find a formula to generate primes. I thought this was my ticket, you know. And I was sure I had a formula, and I was always haunting the QA 500 section of the library, and I knew all the books by heart, and I knew all the authors. And there was one book I really liked, and I picked out this book, and the author, his name was John Selfridge. He was a professor at the University of Illinois, and I actually wrote him a letter. I was like 10 years old. Actually wrote him a letter and said, you know, I believe I've discovered a formula, blah, 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 right? He actually wrote me back a really nice letter and, you know, thanked me for my interest and that kind of stuff, and told me that the number I had sent him was not prime and that it was divisible by these, you know, really big numbers, And there was a sheet of, it looked like a cash register receipt. It was from an adding machine where he did the calculations to show that this number was not prime. And it blew my brain because, this was like, a 15 or 16 digit number, and he had been able to factor it just using an adding machine. And this little printout that he sent me had all the information in there. And so I studied that, and basically this is the kind of thing he was doing, right? He was reducing modulo a factor, and then he just had to do these simple additions and multiplications on small numbers, and he was able to show that something was congruent to 0 modulo this other thing. So this is like a really powerful technique. Even if you don't have a computer, right, you can do large arithmetic with this. But if you have a computer, right, you can do even more. And this is how things like public key crypto systems work. Because to do like an RSA encryption, right, internet commerce, that kind of stuff, you need to do these really large exponential calculations on big numbers. And those are tractable by doing things like modular exponentiation.
Then for the mod operator in C, like at a compiler level, they wrote some algorithm that uses Fermat's little theorem and the modular exponentiation.
No, mod operator is just doing a division and looking at the remainder.
Oh, it just does that.
Yeah. Yeah, because it's small numbers, and it's probably done in hardware at this point. Used to be a big, long software algorithm. But if you have something that would do really big, well, even BC is just doing it by hand, I believe. It's just multiplying it out. Yeah, it does have limits. But it's pretty good. Come on. There we go. Whatever that number was. Yeah, that's a righteous exponent. That's my next password. All right, questions about that? So there's some homework questions on that, right? That have you play with these. So try those before Wednesday.
Would those bigger algorithms for like blockchain or things like that use this software methods?
Probably, yeah. All right, so we've talked a little about prime numbers already. Let me talk a little more about these, and then we'll shift over and start talking about applications of all of this stuff. In computer science, in particular, there's applications that are interesting to us. So prime number, right, divisible only by itself in 1. So how many prime numbers are there? Infinite number, right? And the Greeks knew this. And it's a pretty simple proof by contradiction that there's an infinite number of primes. Suppose the set of primes P equals P1, P2, P sub k is finite. Suppose there's only a finite number of primes, and there's k of them, let's say. And so I can make a finite set P containing all the primes. Okay, well, let n equal the product of all primes plus 1. Well, it turns out that, P1 cannot divide n, because n is 1 more than a multiple of P1. And n is actually 1 more than a multiple of P2, and it's 1 more than a multiple of P3. right? And if I have a multiple of 7 and I add 1, it's not a multiple of 7. I've got to add 7 to get to another multiple. If I have a multiple of 2 and I add 1, it's not a multiple of 2. I've got to add 2 to get to another multiple of 2. So n is congruent to 1, modulo p1, modulo p2, all the way up through modulo pk. Therefore, p1 does not divide n, p2 does not divide n, pk does not divide n. Well, if these are all the primes in existence, n is not divisible by any prime number. We can show from there n is not divisible by anything other than itself in 1. Right? So this would mean n is prime. But n in particular is bigger than each of our prime numbers, and so n is not a member of P, and that's a contradiction. All right, so if there were a finite set of primes, you just multiply them all together and add 1, and one of two things happen. Either you've got a prime number, or you've got something that's divisible by one of your other primes, which isn't possible. So that proves that this set cannot be finite, so there must be an infinite number of primes. So that's a nice proof by contradiction. So there's a thing called the fundamental theorem of arithmetic. Right, there's fundamental theorems of calculus and complex analysis and all this other stuff. Arithmetic has its own fundamental theorem. And what does this theorem basically say? Numbers have unique factorizations into primes. Let's say positive numbers bigger than 1. Have unique factorizations into primes and powers of primes. We could write this very formally and it would be gobbledygook, impossible to read. But here's the basic idea. 36 is 2 squared times 3 squared. 37 is just 37. 38 is 2 to the first times 19 to the first. 39 is 3 times 13. 40 is 2 squared times 5, right? Numbers are either prime, so it's just a prime raised to the first power, or a product of powers of primes. And the fundamental theorem says this factorization is essentially unique. Now, why is it essentially unique? Because I could also say 36 is 3 squared times 2 squared. Isn't that different from 2 squared times 3 squared? Yeah, but not really. Okay, so unique in all interesting ways, right? I could also say this is 2 to the first times 3 squared times 2 to the first. But that's the same thing, okay? What it's telling me is I can't find 36 is equal to, 5 times something or 7 times something, right? So once you break it into primes, you've got a unique factorization. That's the fundamental theorem of arithmetic. And it's a cool fact. We can do lots of stuff with that. And it's not always true for other number systems. And there's a very famous proof of Fermat's last theorem that turned out to be a bogus proof, because in the space where this person was working to do this proof, there was no fundamental theorem of arithmetic. He assumed unique factorization, and it turned out that the space he was working in did not have unique factorization. But by assuming that, he came up with a proof. And eventually people were like, no, you assumed fundamental theorem, and it doesn't apply in this case. And so he tried to fix up his proof by inventing more numbers so that he could restore unique factorization, and he invented new branches of mathematics, something called ideal theory from that. But for plain old integers, this thing is true. All right, so we talked about testing prime numbers with respect to programming assignment 2. You can just divide by every possible number, or maybe every odd number, bigger than 1 and less than the square root of the number, and that's pretty efficient. Here's another way to generate prime numbers. I'm just going to do this a little bit. All right. So write down your integers, okay? We start off, we circle the 2, and then we erase every other number. So we circle the 2, so let's get rid of every other number. All right, circle the next number that's not already crossed out. That would be a 3. And now get rid of every third number. So 3, 3, 3, 3, 3, 3, 3, 3, 33. Circle the next number that's not crossed out and get rid of every fifth number. So the 10, 15, 20, 25, 30. Next number that's not crossed out is a 7. Get rid of every seventh number after that. Next number that's not crossed out is an 11. Get rid of every 11th number. Next number is a 13. Get rid of every 13th number. 17. Get rid of every 17th, 19th, 23rd, 29, 31. There's all your primes. So that's called the sieve of Eratosthenes. And we don't use that to generate primes, but we could. All right, well, we know there's an infinite number of primes. How many prime numbers are there up to a certain point? So if we go up to 1,000,000, we know there can't be more than 500,000 primes because all the even numbers are not prime other than 2. So it's less than 500,000, and we know that every third number is composite except for 3. So it's probably less than a third of 1,000,000. But, you know, at some point, we can't say it's less than, you know, every 101st. You know, at some point, the number of primes that we're just missing starts to overwhelm how much we're chopping out of it. So how many primes are there? So let's make a function. Let p of x equal the number of primes less than or equal to x. And this is for x, you know, say bigger than 1. So people have studied this function. How many primes are there less than or equal to some number x? And there's this thing called the prime number theorem. This is the only time you'll see me do a limit in this class. So the limit as x approaches infinity of p of x over the natural log of x is equal to 1. So the number of primes less than or equal to x is approximately the natural log of x. All right, logarithm base e, where e is that number 2.71828 that pops up all over calculus. Now x has to get really big before this looks like a good approximation. But in the limit, it's exact. So that's pretty cool. Because, I mean, primes are all about integers. And e is this fraction, well, this decimal number. It's irrational. But it pops up in calculus a lot. So we don't have a formula for generating primes. There's no machine. You can just turn the crank and prime numbers pop out. If you find such a machine, you can do all kinds of interesting things in our world. So this is a little bit what Bitcoin mining was all about several years back when everybody was trying to mine Bitcoins. Discovery of large primes is challenging. And we've found some pretty large primes, but we haven't found all primes up to the largest prime we know. There's specific types of primes that are easier to find than others. So look at powers of 2. So 2 to the first is 2, minus 1 is 1. Well, 1's not technically prime, okay? But 2 squared is 3, that's a prime number. 2 cubed is 8, minus 1 is 7, that's a prime. 2 to the fourth is 16, minus 1 is 15, well, that's not prime. 2 to the fifth is 32, minus 1 is 31, that's prime. 2 to the sixth minus 1 is 63, not prime. 2 to the seventh minus 1 is 127, that is prime. Is there a pattern here? What's significant about the exponents of 2, 2, 3, 5, and 7? They're prime. So 2 raised to a prime minus 1 looks like it's often prime. It's not always prime, though. But a lot of times it is. So this is a special type of prime. It's called a Mersenne prime. I think I missed an E somewhere. I missed an N. So Mersenne was a mathematician who studied these. A Mersenne prime is a prime of the form 2 to the p minus 1, where p itself is prime. And it turns out if you have a number like this which is prime, you can tell that it's prime more easily than just dividing by every possible factor below its square root. There's tricks you can use. And so people have been studying primes of this form for a long time. If you look in the Guinness Book of Records, the largest prime known any given year is always a Mersenne prime. So every time I do this, it's a different story, because we keep finding more. Okay, so list of known Mersenne primes. So 2 to the 2 minus 1 was known by the Greeks, 430 BC. 2 cubed, 2 to the fifth, 2 to the seventh, those were known by the Greeks. It took 130 years to get from 2 to the fifth, 2 to the third to 2 to the fifth. But that's probably just when they recorded that fact. And then 2 to the 13th was discovered, 1,700 years later by someone who didn't even take credit for it. And they found that by trial division, dividing by every number smaller than the square root. And then 2 to the 17th, 132 years later, by trial division. And then 2 to the 19th by the same person, same year. And then there's a gap. Say what?
Did you just keep going after the first one?
Probably. Got lucky. And then there's a gap to 2 to the 31st. And Euler found that, right, 100 some years later. Trial division with modular restrictions. So we're starting to use some of these modular tricks, right? And then there's another gap of 111 years to 2 to the 61st, and that's using something called Lucas sequences. So there's this thing called the Lucas-Lehmer test, which was discovered by these two mathematicians that let you test the primality of a Mersenne number more easily than just dividing by everything below it. So now at that point, this sort of takes off. So 2 to the 89th minus 1 in 1911. And these are all Lucas sequences. Here's the Lucas-Lehmer test. We're up into the 50s, and computers are starting to be a thing. So 2 to the 521st minus 1. And these are sequential, okay? So this is the 13th prime for which 2 to the p minus 1 is prime. And so Lucas-Lemur test, different machines that were being used. So now we're in the 60s. And the technology is getting a little better. Here comes the big iron of CDC, Control Data Corporation, to the 21,000. So this is where I kicked into the game as a kid, right? That was the first large prime I found in the Guinness Book of Records, and I memorized it, and I tried to write out its digits and all kinds of stuff. Got 6,002 digits. So Lucas-Lemur test was the main way to check these. Cray, right? Seymour Cray left CDC and started Cray Research. And those were these supercomputers through the 80s. And then 90 megahertz Pentium, right? And this was discovered by something called GIMPS. GIMPS was the Great Internet Mersenne Prime Search. And this was a screensaver you could download for your PC, and instead of showing a Windows icon floating around on your screen, it would look for prime numbers, right? Mersenne primes. And it was all centralized, and your computer would be running this in the background, and if it found a prime number, it would send it back to the mothership, and you'd become famous on Wikipedia years later. So, so all of these primes that come after this are mostly discovered by this collaborative online search, right? So 100 megahertz Pentium, right? My first Pentium was like 75 megahertz. It was like fast. And so these get faster, and these exponents get bigger and bigger. And so now, December 7th, 2018, the 51st Mersenne prime to the 82 million something, a number with 25 million digits in it. And it's just an Intel Core i5.
So I'm assuming that's distributed computing?
Yeah, yeah.
Okay.
Yeah, so one machine is testing one particular number, but each machine's testing a different one, basically.
So they can't divide that up anymore in that?
I don't think so. I think it's one number per machine, but I'm not positive about that. I did learn the Lucas-Lemur test once, but it was a long time ago.
So they're just running the Lucas-Lemur test on this, correct?
Yeah, yeah. So people hunt for large primes, right? Mostly for fun and credit, and not necessarily a lot of practical value in those particular primes. But you know, it's nice to know what the biggest prime is that we know, and we also know there's no biggest one because they go on forever. And you know, these are getting further and further apart, right? The 50th Mersenne has 23 million digits. The 51st has almost 25 million digits. So 2 million more digits. And in general, as you go up, primes get further and further apart, right? Kind of makes sense because there's more things that numbers can be divisible by. But even as you increase your numbers, you still find things like this. You find pairs of primes that are separated by 2. And we don't know if that goes on forever or not. As large as we've looked, we keep finding pairs of these so-called twin primes. Primes that are very large but are separated by only 2. And we don't know if there is a largest pair of twin primes after which all primes are separated by at least 4, or if twin primes exist no matter how large you go. It's an open problem. It's another problem that's really easy to understand, but apparently really hard to prove one way or another. So that's an open problem. Goldbach's conjecture is an open problem. That's your PA2. All right, can we write every even number as a sum of 2 primes? So lots of questions like that. All right, the other thing I'll mention along with primes is perfect numbers. So take a number, write down all of its factors except itself. So 6 is divisible by 1, 2, and 3. And if you add those factors together, you get 6. Okay, what's 28 divisible by? I'll start us off. 1, 2, 4, 7, 14. Anything else? All right, 1 plus 2 is 3, plus 4 is 7, plus 7 is 14, plus 14 is 28. So there are some numbers that if you add up all their factors less than themselves, you get the number back. And those are called perfect numbers. And it turns out 28 is 2 to the third minus 1 times 2 to the 3 minus 1. This is a Mersenne prime. This gives you a perfect number. 6 is equal to 2 to the 2 minus 1 times 2 to the power 2 minus 1, 3 times 2, and that's a Mersenne prime. And it turns out anytime you get a Mersenne prime, you get a perfect number. But we don't know if that describes all perfect numbers, and in particular, we don't know if there are any odd perfect numbers. This is always going to be even because you're multiplying by a power of 2. But are there any odd numbers where the sum of the factors adds up to the number? That's another open question. All right, so the last thing I'm going to mention, because we're going to come back to it probably on Wednesday, is something called the Chinese remainder theorem. So named because it's referred to in some very old Chinese texts, not by the name, but the statement of this is used. So the Chinese remainder theorem is about solving systems of equations where you're working with congruences. And so, for example, consider the following situation. Suppose we know that x is some number which is congruent to 2 modulo 3, and x is congruent to 3 modulo 5, and x is congruent to 2 modulo 7. Is there a solution to these equations, and if so, what's a solution? What is x equal to? And it turns out that if these modulos are pairwise relatively prime, so if any two of these are relatively prime to each other, meaning they share no common factor, which is certainly true if all of these are prime, then there is a solution. And in this case, I think it's x equals 23. So x minus 2 is 21, that's a multiple of 3. X minus 3 is 20, that's a multiple of 5. And x minus 2 is 21, that's a multiple of 7. So the Chinese remainder theorem is an algorithm we can use to find solutions to these equations. And it's also the statement that if these moduli are relatively prime in pairs, then there is a solution. And I'm not going to go through that algorithm, but I want you to know that it exists and it will let us solve systems of simultaneous equations like this, because we'll use that when we do public key encryption, probably on Wednesday.
I feel like I remember back in 270, you were talking about how most float values are only accurate up until a few digits.
Mm-hmm.
Is that relevant to this at all? And how accurate accurate these algorithms that computers are running to find points?
So that was more about trying to represent real numbers with a finite set of bits.
Okay.
So if you have like 32 bits to represent a float, or 64 to represent a double, and you're trying to represent all numbers from 10 to the 300th down to 10 to the negative something, right? There's way more numbers. There's real numbers. There's an infinite number of points in that space, and we only have 2 to the 32nd or 2 to the 64th patterns to represent this infinite number of points. So there's going to be some rounding that takes place.
Gotcha.
So that's more an artifact of real numbers versus integers, I think. All right. So why do we care about all this stuff besides just for the fun of it? So there's applications for a lot of this number theory. So a real simple application, something called parity. So has anybody here ever used a dial-up connection to a computer? Okay, so you dial up on the phone and it makes these squeaking noises and you make a connection. Has anybody ever used an acoustic coupler? So in the earlier days of working on computers, you used something like this to make your connection. Right? It was this device, and your phones, had a base unit and a dial, and then the thing you would pick up and hold to your head and talk to, like this thing. And so you would call up the computer, and after it answered and started making tones, you would take that handset and shove it down onto those two rubber pieces. And it would basically squawk into that bottom section, right, which is labeled chord, and there's a microphone in there. And it would take those tones and send them to the other side, whatever it was connected to. And it would listen on this side and take the tones that come out of that and send it to whatever was connected to this, usually a terminal of some type. And it worked well, right? They were relatively fast. You could do 30 characters a second, right? Sometimes 120 characters a second if you had a fancy one. So this was slow, but for the time, it was pretty good. But it's acoustic, right? There was no no electrical connection between your phone and the thing that was sending this information. And that was necessary because, so the phone company used to be a monopoly, right? Ma Bell was one of the first monopolies. And you did not own your telephone, you rented your telephone from the phone company. Every month you paid them a few bucks for your phone. You could not buy a phone, right? And if you were able to buy a phone or make a phone, it was illegal to plug it into the wall, right? The phone company said, this is our copper, you can't connect anything to that unless we say you can. So that's what a monopoly lets you do, right? And people wanted to do things like, transmit information to one computer from another using the phone lines, and they would get sued by the phone company, and they'd go to court and they'd say, you can't put something on the wire unless you get permission from the phone company. So this went through court a number of times, and finally one of the times it went through court, landmark decision was made, which says as long as you don't actually connect something electrically to the wires in the wall, you can send anything you want. You can transmit any sounds that you like, as long as you're not electrically connecting to the copper. Right? And that changed the whole world, because now you could do things like this, and you could make answering machines, and you could make fax machines, and all of the stuff was commercially available. So you could use this, but it wasn't making an electrical connection, it was sound-based. Which means, if someone comes in and starts shouting, hey, is anybody home? Your transmission gets garbled, right? Because it doesn't know that that's not part of what it's supposed to be sending. So early days of computers, transmission was noisy, right? Of course, the worst case is when somebody picks up the other line and starts talking on it or dialing the phone, and then you usually lose the connection. But just sound level was a problem. So here's the deal. You're sending ASCII characters from one computer to another, right? And I'm entering in grades, and I'm typing in someone's grade, and they got an A. So what's the ASCII code for A? It's that, 65. Well, it's sending out, you know, low tone, high tone, low tone, low tone, low tone, low tone. Someone walks in and slams the door and says, hey, is anybody here? And this changes into a high tone and a high tone. Well, that's the ASCII code for a C. I typed in A, the computer received a C. Guess what? Your grade is a C for the course now, right? So that's a problem. So we needed ways to know if what was transmitted was the same as what was received. Basic error checking. Well, one way is to just transmit everything twice and compare, but that's pretty inefficient. It cuts your speed in half, and at the time, you know, 1200 baud, 120 characters a second, was pretty much top end. So the idea of a parity bit is to send one bit along with your character, which tells you whether or not the character you received is valid. So how does this work? There's two versions of parity, odd and even. So let's talk about odd parity. So odd parity, we want to add one bit such that total number of ones is congruent to 1 modulo 2. So here's the code that I'm trying to send across. I'm going to add one bit in the beginning, which is a parity bit. And I can add a 0 or a 1. I want the total number of ones to be odd. Well, I'm planning on sending 2 ones. That's an even number. So I'll set my parity bit to 1. Okay, so I'm going to transmit 9 bits of information to 1, followed by those 8 bits. Now on the receiving end, this bit gets perturbed, and this number is received with a parity bit of 1. What does the computer do when it receives it? It says, okay, I've got 1, 2, 3, I've got 4 ones. I'm supposed to have an odd number of ones. It says there's a parity error. So you add up the number of ones, you find what is congruent to modulo 2, and if it's congruent to 0, you can say this is not the information that was sent. Something changed. So you say parity error, and that causes the person to resend their original number. And then if this is what's received, you say, okay, that's an odd number of ones. That's a good piece of information. This is also nice because if your communication line happens to go dead and you just start sending off zeros, your receiver will know something's wrong right away, because when it sees this pattern, it should say, hey, this should have been a 1 somewhere in here. There should be an odd number of ones. So this is actually a fairly powerful and really simple way to do basic error correction. And so what's your parity bit? Basically 1 minus the sum sum up all of your digits, reduce it modulo 2, and then subtract that from 1. So if your sum of digits is even, this will put a parity bit of 1. If your sum of digits is odd, this will put a parity bit of 0. So use that to feed your extra bit. So what's the sort of obvious problem with this? Or a sort of obvious problem.
2 bits get changed.
Yeah, if 2 bits get changed, forget it. You're not going to notice. Or 4 bits, or 6 bits, or 8 bits. Right, so it'll pick up a single bit error, and it won't tell you anything about which bit is off. And it could be, you know, the parity bit is wrong. Could be the parity bit got flipped to a 0. It's still going to notice, hey, I've only got an even number of ones. Okay, but that's all it knows. Something got flipped, but it doesn't know which. So you have to resend the whole piece of information, all 8 bits plus parity. But first order error checking, it's not a bad system. And usually when something goes wrong, You know, it's because someone picked up the phone and is talking on it, or there's a solar burst or something major going on. You're going to get a lot of transmission errors in a row. And as soon as you start seeing that, you would know it. And then you can do whatever is appropriate.
Wouldn't the error checking for deadline only work half the time if your number was even or odd?
Well, if it's a dead line, you're going to get all zeros, right? And the first time you get that, if you're doing odd parity, you're going to know that something's wrong.
So odd parity always has a 1.
No, but if you had 8 zeros here, your parity bit would have to be a 1. Odd parity, your 9-bit packet should always have at least one 1. You can do even parity also. And if you play around with older terminal programs, sometimes there's still a setting for do you want even parity, odd parity, or no parity. And that's all it's referring to. Even parity is exactly the same, except you want the total number of 1 bits to be congruent to 0 mod 2. And then there's things like error correcting and checking codes, ECC, which are like this, but they're more sophisticated. So by adding 3 extra bits to every 32, you can do more reliable detection of errors, and you can do rudimentary correction. I think if you have up to 2 bits flipped, you can detect it, and if you have only 1 bit flipped, you can actually correct it just by using this 3-bit code. So early computer memory, when it started growing in density, was suffering from bit flips. Right, cosmic radiation will flip a bit in a DRAM, and so the slightly better memory always had ECC on it, error checking and correcting. And there are always 2 price tiers for memory when you would look to get more memory for your machine. There was non-ECC, which was cheaper, and there was ECC, which was more expensive but more reliable. So that's one application area. Another one which you probably know about if you're in 222 is hashing. Right, so we use modular functions in a lot of our hash generation. Basically take something like a license plate or a name or a binary file or an image and reduce it to some integer. Well, if we're hashing, we're doing that to find a place to store it in our hash table, in our array. But we can also do things like MD5 hashing. And if you go to download a piece of software from the web, from a reputable source, usually you'll see something called an MD5 hash. And it's a big, long, 2-dimensional area filled with hexadecimal numbers, right? It's a large integer that's generated by taking the thing you're downloading and running it through this MD5 algorithm to produce this, 500-digit integer, or however big it is. And why do you want to do that? Because you want to know if the thing you're downloading is actually what it's supposed to be. So if somebody has changed this image that you're downloading, and you load it in your computer and you run it and it installs a virus on your computer, right, that's not good. So what do? You download this piece of software and you run it through your own trusted MD5 hash generator, and you look at the big number that it produces and you compare it to the number that it's supposed to produce. And almost certainly, if even a single bit in that image has changed from what it was supposed to be, you'll get a totally different number coming out of the hash. And certainly if you're going to change the image to do something like, maliciously install a rootkit on your machine or something, it's going to be almost impossible to do that in a way that does not change the hash that comes out of your MD5 generator. So it's an integrity checker. We can also use this idea for doing things like fingerprinting songs. So you have a bunch of songs in your library and you want to add tags to them, so you go to a database, and it basically takes your music and it runs it through something like a hash to produce a short integer that corresponds uniquely to that piece of music, and now it can search a database of these integers and see which songs they belong to. So like Music Brain's Picard, right? And so it's a way of fingerprinting. And you don't want to take your entire song and upload that and compare it to a database of, 80 megabyte files, because that's just a lot of data to process. So you turn it into a short integer, and you can use that to look for the identity of the song and then download the tags from a database.
For Dropbox even uses that for duplicate
Oh,
files. So if you try to put the same
oh, cool,
the YouTube
okay.
video on Dropbox, they actually have a way of checking that and not actually just giving a link to it
Cool.
internally.
Okay. I'm guessing that's what YouTube does too, because they always snag duplicates. And I think this is also how they do like copyright infringement, because they auto grab stuff, and it's just fingerprinting basically. That's cool. I didn't know Dropbox did that. All right. So these little codes that you see, these barcodes that you get on products, so have you ever wondered about those or messed with them? Right, so UPCs, universal pricing codes. So digit, 5 digits, 5 digits, digit, right? So what does this mean? There's a product class. That's 1 digit. So food, clothing, that kind of thing. There's a manufacturer. That's a 5-digit code. There's a product ID. That's a 5-digit code, which depends on the manufacturer. So that's 11 digits. And then there's one more digit, and that's a check digit. And the check digit is there to let you know if you're typing this in by hand, right? No laser scanner. You type in 7722252103330 and a 7. If you make a mistake, right, and it accidentally rings up as a Samsung 54-inch TV, right, and they charge you X amount for this bar, right, or vice versa. Yeah. So you want to know that. So there's a check digit built into this, and there's an algorithm for generating that check digit. And the way the algorithm works, this will catch errors in the numbers that you've typed in, but it will also catch transpositions. So if you accidentally type a 2-5 instead of a 5-2, right, that's a very common key punch error. This should pick that up. So how do we calculate the check digit? So let's write down our I haven't tried this, so I'm playing without a safety net here. 7222252103330. All right. So we have 11 digits. So take your odd digit positions and add those together. So 7 plus 2 plus 5 plus 1 plus 3 is 10, 15, 17, that's 18. Take your even positions. I missed one. Your even positions, so 2 and 2 is 4, and 2 is 6, and 3 is 9. And then take this one and multiply it by 3. So that's 54. Add the 9, and that's 63. And then reduce it modulo 12. This is not going to work. Oh, maybe it is. So what is 63 modulo 12? 12 times 5 is 60, so 63 is congruent to 3. This is what you get for... okay. And then, so it's 3 times the sum of the odd position, plus the sum of the even position. And you do that modulo 12. And then if not equal to 0, subtract from 10. Modulo 12 doesn't feel right. Modulo 10. Okay, so 63 mod 10 is 3. And if you get 0, you leave it as a 0. Otherwise, you subtract it from 10. Okay, so 10 minus 3 equals 7. Right, that's the check digit. So add up 3 times the digits in the odd positions, add up the digits in the even positions, reduce modulo 10, and then subtract from 10 if it's not equal to 0. That's your check digit. And if you transpose 2 digits, right, this one will get multiplied by 3 and that one will get multiplied by 1 instead of the other way around, and it should detect that.
What was the purpose of the check digit again?
Check digit is to know if this number that you've typed in is valid.
Okay.
Right, so if we change this digit to a 1, right, then we would end up adding an extra 3, which would give us 66. Mod 10 is 6. Subtract that from 10, we should have a check digit of 4. And the check digit is 7. That tells you there's an error.
That's if you're typing it in with hand?
Yeah. Or if something changes it.
So I've had to type them in at work before by hand, and we usually don't use the check digit.
Oh, really?
Yeah, you don't type it in. And that's
Wow.
every place that I've worked.
So how do you know if you type it in correctly?
Or we could possibly buy a candy bar that charges the same price.
No, it just won't work.
Unless, I mean, so the thing is that, you know, those 5 digits are a product ID, right? So product class manufacturer, probably fairly resilient, but, you know, there can certainly be consecutive product IDs.
Yeah.
So, yeah, I wonder why you wouldn't use the check digit.
Yeah.
But you were actually typing them in by hand?
Mm-hmm.
Interesting. The other thing is it makes it a little harder to change these, because if I decide to add an extra bar in here or white out part of a bar to change it into, you know, from a TV to a candy bar, I also have to correct the check digit.
Yeah.
And so it's a little harder to do. All right, ISBN codes are the same idea. If you look on the back of a book, there's an ISBN code, and there's different versions of ISBN. There's 9 character, and I think there's 13 character, and so on and so forth. But that's another algorithm. ISBN, you basically use a position-weighted sum of the digits. So the first digit plus 2 times the second, plus 3 times the third, and so on. And you reduce it modulo however many digits you have, plus something, and that gives you a check digit. And same idea, you can use that to validate the number. Questions? All right, so Wednesday I want to talk about crypto systems. So we'll talk about the general ideas of encryption and why we do encryption and what some of the techniques are for encryption, starting with Caesar ciphers, which go back, you know, thousands of years, and working forward, and eventually we'll work up to public key systems, which is what we use basically anytime you do anything on the internet and you have a little padlock up there in the URL, you're using a public key protection system basically. So we'll play around with that on Wednesday, and that will probably finish us up for number theory, and then we'll go on to start talking about counting. All right, so I'll see you next time.
Okay, so I have a question on modular exponentiation.
Okay.